So let's get started. Our talk will be divided into 4 parts. The first part is the background. We will introduce the Pickle platform and the Open Harmony to you. And in the second part, we will spell our work porting the Open Harmony system to the Pickle platform. And in the third part is the difficulty we see importing a system, maybe including some difficulty our friends in real see also. And in the fourth part is the binary translation. Binary translation is maybe a solution for the difficulty we see importing a system. As you can see, the real part is the Open Harmony. This is the pure software stuff. And the red part is the Open Harmony, and up on the red part is the user-defined application, and below the red part is the trusted hypervisor. And on the bottom of the architecture is the Pickle hardware, and everything is run on the Pickle hardware. Open Harmony is the open source project originated from Huawei company, and it launched at Open Autumn Operation for a wide range of devices from 128 kilobytes to 128 megabytes. LSM is a portion of the Open Harmony project. It targets on devices with few resources. For example, maybe MCU, or for example, your memory also only have 128 kilobytes. It's a lightweight operating system based on real-time kernel. So Open Harmony has following feature. It got lightweight kernel. It has small kernel size, small power consumption, and a faster response. It got sensor framework. It has low delay, higher precision, and intelligent sensing. Its connectivity engine got more protocol, wide connectivity, and intelligent connection, and its operating engine got light framework, better performance, and intelligent application. So this is the Open Harmony LiveOSM architecture. On the top layer is the application layer. At the application layer, we run user-defined application. And the user-defined application will use the KAL, HAL, say kernel abstract layer or hardware abstract layer interface to invoke the kernel services or hardware services. At the layer below the application layer is the hardware abstract layer. At the hardware abstract layer, provide a uniform API for application layer. And at the HAL, data structure will be transformed and to invoke the internal API, driver API, and at the HAL, it will manage the hardware driver handler. For example, you maybe got multiple hardware instance. You will need to manage all the instance. The job is done at the hardware abstract layer. And below the hardware abstract layer is the hardware driver. For example, the UART, the timer, the FPI, the GPIO at this layer. And you will need to control and configure the hardware through writing a specific register address. For example, you want to configure the UART, you will need to write a specific value to the certain address space of the register. Then below the hardware driver is the kernel abstract layer. Kernel abstract layer will provide the basic kernel service, for example, sleep, memory alloc, and at the bottom of the home architecture is the Pickle. So this is the timeline of our work. First, we modify some code in the kernel and run it in the Spike to simulate, and then we we try to run it on the board, and we use UR to output the information in the console, and then we, after the kernel it can work on the board, we port the driver, for example, the GPIO, the iPhone C, SPI, timer, port the driver to the system. Then we update the home system, the hardware driver application to the official application interface to provide a uniform API for example, the user layer application to invoke. So this is our demo. Okay, 声音没开，声音。能听到为什么没声音的？啊，看。
真情。
That's our people actually. That's a subset number. That's a real silicon too. It's a 20 part of it. So I have a 5 port.
Slowly. So we see many difficulties in porting a system. The first is the assembly translation. The OS code can contain both C code and the assembly code, as you know. For example, the context switch, the interrupt, the booting, and all these require register level schematic. They are all written by assembly. So when you port a system, maybe visual keys to port the assembly to the RISC, and you need to write the assembly. But the fact is, there are very few assembly programmers, which means this is a very huge obstacle for people to port system from other instruction set architecture to RISC-V. And the second problem is my friend Xiaoyong met. Is the problem of package reference. When you call a huge system, sometimes the huge systems sometimes are related to hundreds of packages, and some package doesn't support to RISC-V. So maybe you need a code to compile it. But the problem is not all the code not all the packages open source. Maybe you cannot get a code. That means you maybe need to rewrite the package with C code and compile it with maybe RISC-V toolchain that require huge workload. And in another case, maybe you got luckier. Maybe the source code of the package is open source. You maybe only need to build it, but building it also take efforts. For example, maybe you need to rewrite the makefile for RISC-V, and maybe in the dependency also, the dependency of the makefile also have the package reference problem. And another cases is some packages support RISC-V, but the version doesn't match. Maybe earlier version is required. This also add the workload for the program. So what if we have a tool that can translate other ISA binary to RISC-V? For example, if you got a ARM binary, maybe there is one tool you can directly include the ARM binary and output the RISC-V binary. If the tool exists, maybe the assembly translation problem and the package reference problem are no longer exist. That will relieve the burden of programmer. That will lower the threshold of porting the infrastructure system to RISC-V. So in the real world, does this powerful tool exist? Excellent example is the Apple M1 chip. In 2020, the MacBook Air and the MacBook Pro use the Apple M1 chip, and the Apple M1 chip has achieved a great commercial success, recording industrial leading performance and efficiency in popular benchmark. One point we should notice that Apple M1 chip use ARM architecture. So how does it run the x86 program? Since we know that most of the macOS platform programs are x86, so how do Apple solve the ecosystem problem? The answer is the Rosetta 2. Rosetta 2 is a tool for macOS to translate the x86 to ARM. Say you maybe want to run an application, but the application in the maybe App Store is x86. You download it, and the Rosetta 2 will help you to do a translation to ARM version binary. Then you can just directly run the ARM binary on the M1 chip Apple machine. So currently the Rosetta 2 support the JIT and the AOT compilation, and the performance of the M1 chip outperform Intel x86 Apple machine in some benchmark, and it supports most of the software now. Overall, the Rosetta 2 received quite positive review. So what if we have a RISC-V version of Rosetta? I think that will be a very big deal for the RISC-V community. So is there a RISC-V version of Rosetta? The answer is no currently. And we do some investigation for the binary translation work, and found that currently there are two types of binary translator. The first type is the work that directly translate the assembly to the target assembly. The second type is that will leave out the binary into intermediate representation, use the target code backend to generate the target assembly or binary. So let me introduce the first method is direct binary translating. The first you maybe got a say binary, and you do disassembly and turn that into the assembly, and you put the assembly into you pass the assembly into a pass tree, and you do some maybe register mapping. You swap the register name into the RISC register name, and then you do a instruction classification, and it translate each instruction into the directly into the RISC assembly, and then you output a RISC binary. The advantage of this point-to-point method is that the target output is small size, and the mapping rule is distinct. It's easy to debug, and the drawback of the method is that you cannot use a compiler optimization target on IR, and it's the point-to-point method. It doesn't have enough scalability. The second method is the IR-based method. The advantage is that it's easy to extend. I should first introduce the method. Maybe you got a x86 ARM or MIPS binary. You lift them up to the QMU TCG IR, and then you maybe go through the LLVM. You translate the QMU IR to the LLVM IR, and then use the LLVM IR to the backend of LLVM IR to generate the RISC binary or assembly. The advantage is that the translation is easy to extend, and you can do optimization on the intermediate representation. The drawback of is maybe the IR you generate is less consistent with the original code, and you will produce a lot of irrelevant code. So we found that the limitation of the current tool is that there is no end-to-end binary translation tool for RISC-V. I think most of the tools are targets. The targets of most of the tools are translate between ARM and x86. And the second point is they cannot translate a system level program. Most of them are just target on the user level program. The system level program will be much more difficult and complicated than the user level program. And the third point is there are many restrictions on the input binary. For example, if you want to use a tool, for example, translate the ARM to x86. First, you may need to compile the ARM code using a lot of GCC flag, and the GCC version may be also qualified. Then you will use the tool to do translation. But if you don't do that, maybe the tool will go error. So in the real world binary, they don't have so much flag and restriction. So this is also a problem. Another problem is the low efficiency of translation. In some tool, you write a few lines of some assembly code, then you use the tool to do translation, and finally output hundreds and thousands of lines. So the efficiency is also a huge question. So what we want to develop is maybe an end-to-end tool. The input is ARM or x86 binary, and the output maybe is the RISC binary, which can run on real silicon without modification. And so it should support both user level and system level program. The RISC binary generated by this translator should be as fast as possible. So our plan could be divided into 3 stages. The first may be the user level target. First, maybe a very simple hello world. Then it may be more complicated, maybe a user level program, and then you maybe we target on the system level program, the light OSM or the more complicated system level program. And finally, in the final stage, I think maybe we should do some optimization on the tool. So I think that's all. So you got any comment since the project have just started? So any comments is very, very welcome. And thanks.
So your approach is the direct translation, or is it a bit to intermediate?
I think our final purpose is to do a default job, since the direct translation is lack of scalability. Yeah. Yes, if you just change a little bit, maybe a whole new need to be developed. Right. Maybe the standard will be a little bit faster. And yeah. So we work on EA to have any common on that. So we have EA suggestion. I'm also curious from the runtime translation. Runtime translation. Yes. So we in our side we put the options the VA and it's the LVA. Maybe yes. We heard that the VA has some advantage in performance in some aspects, and perhaps using we didn't see people use VA to do this well. Yeah. So yes, maybe VA and the runtime is a good choice.
Okay, thank you very much. So just a little bit to your question, I think for the same version that is like a non-dynamical link library, it's okay to put everything down dynamically, but for after we have the link dynamical link, so we cannot just do it in one time. So that's the problem that we need to have a state version to actually force the link one by one. So far, it's like what Xiaoyong is doing. To make this work, and then we can just, like I said, convert to binaries because I already have all the links ready. So that's probably the answer to the question.
Yeah.
小的，我听那个周总说有问题多点，因为我觉得这个工作的看起来一个就是很有意义，但实际上可能并不是。因为这地方我们曾经也见过几个这样的系统，一个是安肯，它是 I64，它后来给我们投486，它在我用了一个全新的。
用了个什么
？OK。自己的在 ID1 和 ID2， 它开始提了。 他以前他把这个 IS3后面考虑做了 IS4， 这个后面专门他也是做了一个手表，然后呢性能差不多，就同样的东西，我在 IS3， 我在 IS4， 这个它性能上会有提升数量级的，是一个。第 第二一个就是说呢，这个地方就是说有些你是先转后运行，还是当场转当场运行？我估计就是先转后运行，是吧？
对，就这个事情就是说 ，this case is the Rosetta 2 is have both option， 就是它两个选项都有。对。
当场转当场运行，
其实就是它这两个选项都有，对，而且可能是运行，就是有可能是运行是问题的，就会有。
另外一个系统运行方式，
是很难转，就是
你现在能转的话，那你自己可以把手。
因为你会觉得在有些个超分领域的话，很多这种 legacy 的这种程序，它就只有单人。
超分对吧？不是以超分，
就是如果我已经有 source code，那我就可以看到这种网络的
超分领域，它不是个大的网络，是一个转换，而是一个多的一个。反倒是问题，其他很多小程序，它自己这个，它一个小的一个转换权，那问题就是慢，和效率低。
对 system level 的话就会有很多，就是比如说 driver RISC。
越是它system level，
对，这个是。
也就是说，你是属于一个简单的应用程序，可能还好，就是效率问题。
对，是系统领域就是会难很多，因为它有很多任体，还有那个，还有一些专门的。
一个程序在多个可以用上嘛？你这样可能对，就是单个的，多的。这个还是我觉得这个路子应该是能走的，路子肯定能走。那就是一个是必须是底层跟和直接相关的底层部分不干活。那可能不一定会转对。这是第一个。第二一个就是说呢，对于多核人和核之间存在很多的这个因素。这个存起来，这个不好使。这个基本上这个。
So now we have configured tomorrow 30 minutes. So continue the session. So thank you.
最后补充几个，就我们这个项目其实是刚刚开始的，就是如果大家感兴趣或者有任何建议的话，都可以给我们这个邮箱发一些您的建议，然后可以接受一下。谢谢。
开了呀，开了。